1227 somewhere.
Maybe. Yeah, you're right.
I guess, you know, there are quite a few people online, so
Yeah.
I'm going to go ahead and start the introduction here. It's a pleasure to welcome Juliane Schwendike from University of Leeds here to give a seminar at NCAR. Juliane got her PhD at Karlsruhe Institute of Technology in 2010 on formation of tropical cyclones off the coast of West Africa. And she spent some time at a postdoc at Monash University in Australia. And then right after that, in 2014, took a job at University of Leeds. And her talk today is going to be, as you see, on the structure of Borneo vortices. Looking forward to it. Thank you very much. Why don't you go ahead and get started?
Yes, so the topic of my talk is examining the structure and dynamics of Borneo vortices. And this work was done as part of 2 projects, and they were funded through the International Science Partnership Fund via the Met Office. So Borneo vortices, they are a synoptic scale phenomenon in boreal winter over the maritime continent, and the surface conditions are characterized by northeasterly winds pretty much always everywhere in the northern hemisphere, and we have westerlies south of the equator. And the northeasterlies, they are often strengthened by the occurrence of cold surges. So you can already see the background climatological state is cyclonic in this area, so any disturbance in this area can develop relatively easily into a Borneo vortex. So the first thing is, what are Borneo vortices? Now, an example of a Borneo vortex is shown here on the right-hand side. You can see the Borneo vortex in the streamlines. The star indicates the center, and you can see the precipitation to the northwest of the vortex associated with the vortex. Now, in the literature, there is no clear definition of what a Borneo vortex is. Most of them, they occur in the northwestern part of Borneo, but there are also vortices that have a similar structure that move in an east-westward direction through the South China Sea. Generally speaking, they are vortices that are confined to a lower part of the troposphere, and they often are quasi-stationary. But if they're located close to Borneo, as in this example, their circulation doesn't have to be closed on the eastern side over Borneo. We care about Borneo vortices because they bring heavy precipitation to Peninsular Malaysia, to southern parts of Vietnam, and to Thailand, and of course to Borneo itself. What do we know about Borneo vortices already from the literature? So an example is shown here in this slide where the figure was taken from the paper by Chang et al. And what you can see in the top row is, in shading, the convective initiation. And at the bottom row, we have the horizontal divergence close to the surface, as well as the horizontal winds. If we start at the top left, we can see in the case that we have no cold surges present and no Borneo vortex present, the convective initiation. So the light green, or generally the green colors, they show us convective initiation. And you can see it's occurring over Peninsular Malaysia, parts of Sumatra, and also Java. And that where we have the convection, there we get low-level convergence. If we have the situation where we have no cold surge but a Borneo vortex, you can see a distinct increase in convective initiation, and the location of that is shifted to the northern parts of Borneo and really into the South China Sea. And again, that goes hand in hand with a low-level increase in low-level convergence. If we have cold surge conditions but no Borneo vortex, then there's another shift in the location of convection. Now it's located pretty much over the big islands in this region. And you can also see this in the low-level convergence, and you can also see the cold surges in this region. If we have the combination of both cold surge and Borneo vortex condition, you can see we get the highest amount of convective initiation, and the center is, or where it's located, is shifted again, and now it's in the northern part of Borneo and over the South China Sea, and you can see with the strongest low-level convergence near the surface. So along with these changes in convective initiation go hand-in-hand changes in rainfall, and these are linked to the presence of, due to this cold surge, due to induced shear vorticity and moisture convergence near the Borneo vortex. The Madden-Julian oscillation can also impact cold surges and Borneo vortices, and this was taken from a paper by Lim. And what we see here are the precipitation anomalies averaged between November to February over all the cold surges in the region. And you can see here we have a positive, so that means an increased rainfall over the South China Sea, affecting northern and western parts of Borneo, Peninsula Malaysia, and even parts of Sumatra and the sea just north of Java. During MJO phases 2 to 4, over the same region, you can see the active envelope of MJO convection and the anomalous winds, and you can see they're weaker, but they're also in the opposite direction. So that means the active MJO phase reduces the number of Borneo vortices and also the cold surges. If we combine them, we still, cold surges and active MJO, we still get an increase in precipitation, and that's linked to the moister and less stable conditions associated with the active phase of the MJO. There are a couple of case studies where people investigated extreme precipitation events that are associated with Borneo vortices. An example is this paper here from OI, and you can see where the vortex is located. But what we don't know in the literature is much about the structure and the characteristics of these vortices, particularly on the different large-scale drivers. So the aim of this presentation is to do exactly that, to investigate the structure of Borneo vortices under cold surge conditions, MJO, and different equatorial phases, waves, and also to investigate, can they also cross the equator? And then we want to focus on one particular case, and this is the one shown here, where a Borneo vortex moved in an east-westward direction through the South China Sea. And we want to look at more detail in the three-dimensional structure of the vortex, investigate if the winds and the temperature are in balance, what the role of diabatic heating was during this case, and what the mechanism was for the formation of the vortex, its spin-up, and its propagation. First of all, we have to identify Borneo vortices, and we do this in era 5 reanalysis data between 1979 and 2021. We look at the period October to March, and we track them at 850 and 925 hectopascals. So everywhere in this red box shown here, the vorticity needs to exceed a threshold for at least certain points during its lifetime. We removed all tropical cyclones from the data set, so not to include any of those. Then another condition is that we need to track them for more than at least a day, and the track at 925 and 850 need to overlap for a certain part of its time. And then they identified as a Borneo vortex. And the tracking has been carried out with the track algorithm by Kevin Hodges at the University of Reading. Once we have the center of the vortex, we take a 4x4 degree box around it, and we look at all the GPMI merge precipitation that is then associated with that vortex. The equatorial waves we are getting from the data set by Young et al., also from the University of Reading. This is based on zonal meridional wind at 850 hectopascal, and were calculated based on era 5. And we're focusing here on the Kelvin wave, the westward moving mixed Rossby gravity wave, and the n=1 Rossby wave. We also need to identify the cold surges, and we do this by looking at the daily mean winds at 925 hectopascal. So when the winds are going through this red line here, then it is an easterly surge. If they're moving through this red line here, then it's a meridional surge. And if they're moving in this box that is just positioned south of the equator, then it's a cross-equatorial surge. And we're also distinguishing the different types, strengths of surges. So we have a strong surge if the winds exceed 12 meters per second, moderate if it's between 10 and 12, and weak surges if their winds range between 8 and 10 meters per second. And for cross-equatorial surges, we're relaxing this criterion a little bit. Here, the winds have to exceed 5 meters per second. So what do the Borneo vortex tracks that we get look like? And this is shown in this plot. So if you focus at the top row, where we got all the different tracks, but they look very well, they look all clumped together, basically. So what we've done is we applied k-means clustering, and we got those 3 clusters. One cluster shows the tracks all moving in an east-westward direction through the South China Sea, and that's what we call the South China Sea cluster. And then there's another one where they move in the northwest region of Borneo. And there is another cluster which contains about 57% of the vortex tracks, and they are all located in the northwestern part of Borneo. But there's still a lot of them. So we subclustered this cluster 1, and this is the 3 subclusters we got. So one, you can see that the tracks, they really follow a C-shaped curve and they move quite far into the southern hemisphere, all the way to Sulawesi. And there's another track, and this is what we call the C-shaped cluster. Sometimes I just call them C-shaped vortices, but this always refers to the shape of the track. Then we have a cluster where the vortices occur in the western part of Borneo, and you can see these are clearly the ones that are more quasi-stationary. They don't move very far. And there's a cluster where they're moving in the northwestern part of Borneo, much closer to the sea, and in the northern Borneo vortex cluster. And it's these 5 clusters that we're going to investigate in a bit more detail now. But before we do this, we just want to look at the climatology of these. And you can see this here for October to March, and then plotted is the track frequency of the different vortex types. And you can see that early on in the season, we get a higher number of those South China Sea vortices, then their occurrence tails off during the season. We get they're peaking in November, we get an increase in the northwestern Borneo vortices, and then it's tailing off. And later on in the season, the C-shaped Borneo vortices are increasing, peaking in January, and then decreasing. So it's a clear seasonality, and you kind of can see that as we go through the season, they are moving further south. So the first synoptic driver that we're investigating are the cold surges. What you have here is the vortex track frequency under different cold surge conditions. So at the top left, we have no cold surge conditions. So Borneo vortices can occur even if there are no cold surges present at the time. And you can see the maximum is over the South China Sea, but if you look at the gray shadings, you can see they're affecting southern parts of Vietnam, Thailand, and definitely Peninsula Malaysia, and also Borneo. With any type of surge, you can immediately see we get a distinct increase in the number of Borneo vortices in any of those surges. If we have cross-equatorial surges, you can see that the distribution of the tracks is in the C-shaped clusters. So the cross-equatorial surges are favorable for the C-shaped vortices to occur. And if we have meridional and easterly surges, the distribution is relatively similar. They're affecting western Borneo, northern Borneo, in both cases, Peninsula Malaysia as well. And we can now look more closely and how the cold surges affect the initiation, the track, the rainfall, and the maximum relative vorticity. And we distinguish now between no surge condition, weak, moderate, easterly, meridional, easterly, and cross-equatorial. And the colors for the different clusters are always the same throughout the whole talk. And if you see a little red dot on top of the histogram, then that means the anomalies are statistically significant. So if we start with initiation, you can see that if we have, in case of no cold surge, it's not favorable for any of the wave clusters except for the one in the South China Sea. And as we increase in strength in Borneo vortex, the number of the different clusters seem to increase. We get a maximum in the northern Borneo vortice cases when we have the combined meridional and easterly surge. The other thing you can see is that these strong surge and cross-equatorial surge conditions are not favorable for the vortices that move in an east-westward direction. We also get a modification of the track. So we see the same behavior in the no surge conditions. And again, you can see the stronger the surge, the stronger the impact of the track. And we get here for the strongest surges, the biggest impact on the northwestern Borneo vortices. And you can also see from this track that really the cross-equatorial surges they are linked to the C-shaped Borneo vortices by far. The cold surges are also modulating the rainfall associated with the Borneo vortices, and it's negative for all the vortices under no surge conditions. And again, the stronger the cold, almost true, the stronger the cold surge, the larger the impact on the rainfall. And you can see here a maximum for meridional easterly surges for the northwestern Borneo vortices again. The picture is clearer for the relative vorticity, which is probably what you would also have guessed, that the cold surges, the stronger they are, they lead to a increase in the strength of the cold surge, I meant the Borneo vortex. So the stronger the cold surge enhances the relative vorticity in the region, and therefore the Borneo vortices tend to be stronger. And for the vortex case where this is not true, is the South China Sea vortices, but it also makes sense because they don't want a strong equatorial flow or northeasterly flow. They just want to move in an east-westward direction undisturbed. So we've done the same analysis for the MJO conditions, and that's what you can see here. And we binned them here, the active phases 3 and 4, the other active phases, inactive phases. And just to make the comparison easier, you have the cold surges impact that we just seen, and we have the combined active phase of MJO and cold surges. And what's most interesting maybe is, well, first of all, the impact of the active phase of the MJO is slightly positive, except for the South China Sea vortices. And if you combine the cold surges and I wanted to say that, yeah, if you combine the cold surges and the active phase of the MJO, we get the biggest modulation in the track. And if you look at the others, we also get the biggest modulation in rainfall and also in relative vorticity. And maybe not unsurprisingly, you get an increase in rainfall that is similar to what we've seen from this other study at the beginning, an increase in rainfall for all vortex types, and almost all vortex types also an increase in the relative vorticity during the active phase of the MJO. Then we've done the same for the equatorial waves. So now you see the initiation frequency at the top row, track frequency at the bottom row, and then we look at Kelvin waves, westward moving mixed Rossby gravity waves, n=1 Rossby wave. And you have a little cartoon at the bottom of each plot to make it easier to see in which type of the wave phase we are in. So if we look at initiation frequency, we can immediately see the biggest impact comes from the westward moving mixed Rossby gravity waves. And you can see, for instance, in the phase where we have the positive phase to the left, the negative phase to the right, for all the Borneo vortex clusters, that leads to a decrease in initiation. But if we're in the opposite phase, that leads to an increase. You can also see that the n=1 Rossby wave are modulating the Borneo vortices. But slightly order of magnitude is the wrong word, slightly less strongly than the mixed Rossby gravity waves. When it comes to the track, it's also those two that have the biggest impact on modulating the track frequency. For instance, if we're in the negative phase, and it has for almost all except the C-shaped vortices a negative impact, and if we're in the positive phase, it has for all of them a positive impact. And if we now look at the n=1 Rossby wave, we can see that if the negative phase is to the north and the positive phase to the south, then for the South China Sea and northern Borneo vortices, all of them except the C-shaped vortices, it's negative. And if we look in the opposite, it's exactly the opposite response. Let's look at the modulation of the rainfall. So here the picture is ever so slightly different because it's the Kelvin wave that have the biggest impact in modulating the rainfall. When we are in the converging phase, we get for all the different Borneo vortex types a decrease in rainfall, and if we're in the convergent phase, we get an increase. And if you look at the orders of magnitude, it's much bigger than for the other two wave types. However, having said this, the response in modulating the rainfall of all three waves is of the same order of magnitude than it is from the cold surges, where it wasn't true for the previous slide that I showed you. And that's maybe not so surprising because the cold surges, they last for several days. They have much longer time to interact with the vortex, whereas the different wave phases, they're more transient and they move through this region more quickly. If we now look at the maximum relative vorticity, then it's again mixed Rossby gravity waves and the n=1 Rossby wave that have the biggest impact. So we see if we're in the negative phase of the mixed Rossby gravity wave, then that leads to a decrease in vorticity and an increase if we're in the positive phase. And if we're in the in the n=1 Rossby wave, if the negative phase is to the north, positive phase to the south, we get mainly a decrease and mainly an increase in the opposite phase. So what the equatorial waves are doing, depending on their position, they can strengthen the northeasterly flow and therefore enhance the vorticity, or they can, depending if they're positive phase, they can enhance the relative vorticity of the Borneo vortex, or if it's the negative phase, then it can weaken it. So here you see a snapshot of a particular example of the 5 clusters that I've shown you before. And we have an example for a C-shaped Borneo vortex, one in the western part, and all the other regions. And as well, you see the accumulated rainfall over their lifetime. And we want to look a bit more closely at 2 examples. One is the C-shaped cluster and the South China Sea cluster. And I picked these because they are maybe not your garden variety Borneo vortices that you typically think of when you think of Borneo vortices. So if we're starting with the C-shaped cluster, This is one that occurred in January 2019, and we look at these streamline plots. You see in pink the track of the Borneo vortex at this particular time. There's a bit of precipitation associated with the vortex. 2 days later, it's located. The precip is located on the western side, and then you can see this vortex moved far into the southern hemisphere, affected going all the way to Sulawesi, and was associated with a lot of precipitation. And this vortex led to a lot of flooding and heavy rainfall in Sulawesi. If we characterize the vortices a bit more, let's look at this top left plot. So this is the time series and then height on the y-axis, and the black line shows us the height of the vortex. So you can see that there's a variation in the height throughout its lifetime, but on average, it was confined between 400 to 500 hectopascals. The green lines show you the vertical tilt, so dashed line is north-south tilt. The dotted line is the east-west tilt. So for most of its lifetime, there wasn't a lot of tilt except towards the end. And you can see here when it moved into the southern hemisphere. So it almost spent half of its lifetime in the southern hemisphere. At the bottom, you see the equivalent plot, but this time we have the relative vorticity following the vortex in the black line, and it's during its whole lifetime. And you can see the precipitation throughout the lifetime. And we can see the peak at the beginning and then more two substantial peaks later on in the lifetime. And if we now want to look at this Hofmöller plot that is shown here, the time is going up, and shown in this Hofmöller plot is in shading the rainfall, and we have in stars, or in the magenta stars, the position of the Borneo vortex. And the different lines are corresponding to the different equatorial waves. So at the beginning, the vortex was not interacting really with the wave, but then it interacted with the positive phase of the convergent phase of the Kelvin wave, and we get a slight increase in precipitation. Then it interacted with the divergent phase of the Kelvin wave, and you can see we get some precipitation from that. And towards the end, it was the interaction between the convergent phase of the Kelvin wave, and also, if you look closely, we are in the negative wave of the n equals 1 Rossby wave. So at different times of the lifetime of this particular Borneo vortex, it interacted with different types of waves. Another example is shown here. This is now a South China Sea vortex, and you can see its entire track here. Even in its early stages, just off the west coast of the Philippines, it was associated with precipitation. You can see it moved over southern Vietnam and then into Thailand. You can see the heavy precipitation that it caused in Vietnam and also led to heavy precipitation in Thailand. The plots are the same. So roughly, this vortex here in this characteristic metric reaches a height of also 500, but at times went up to 300 hectopascals. You can see that the shear was much higher here, and we shall talk a bit more about the impact of the shear in a couple of slides. And if you look now at the relative vorticity and the precipitation, they are much more aligned, and generally this Borneo vortex brought a lot of precipitation, as I already pointed out. So, and you can also see in this plot here that there was already another east-westward moving Borneo vortex following as the other one reached the end. We want to now spend a bit more time thinking about this vortex in more detail. And here's another snapshot for two particular times that show you the streamlines and the relative vorticity on the 23rd of October and the 24th of October 2018. You can see the center of the Borneo vortex in pink at 850 hectopascal and in turquoise at 925 hectopascals. And you can see on the 23rd, the vortex was located in the middle of the South China Sea, clear signature and relative vorticity. And 24 hours later, it moved in the westward direction and was now further in the South China Sea. We were interested particularly in this case because it led to flooding, landslides, and warning of rough sea in the southwestern part of Thailand. So we are going to investigate this case in a bit more detail using global and convection permitting METUM simulations. The global simulations have a grid spacing of 18 kilometers and the convection permitting simulations of 4.4 kilometers, where obviously the convective parameterization is switched off, and they have been nested into 10-kilometer global simulations. The runs were initialized on the 21st of October 2018, run out for 12 days, and the start time was 12 UTC. And another tool that we're using to analyze these simulations is called the semi-geotriptic balance tool. And that was developed by Mike Cullen at the Met Office and is summarized in this paper in 2018. So what is this tool doing? So it's basically an extension of the semi-geostrophic balance, but in the boundary layer, it's also accounting for friction. So in the free troposphere, you have the balance between geostrophic force and pressure gradient force, so typical geostrophic balance. But in the boundary layer, we have to account for friction, and therefore we have a balance between three forces, and we're using semi-geostrophic theory. So this is called semi-geotriptic balance, and the tool calculates that for us, basically, okay, does these calculations. And the advantage of using the semi-geotriptic balance tool is that that we can calculate the three-dimensional ageostrophic flow that is associated with the SGT balance, and we can partition the forcing into that from diabatic heating, geostrophic forcing, and friction. The tool has been applied in the mid-latitudes, but we're using it for the first time in the tropics. So let's have before we dive into it, let's have a look at how well are these model simulations representing reality. So on the right-hand side, we have GPMI merge precipitation. Here you have in purple the track of the vortex, and the star always indicates in all the plots where the location of the vortex is. And we can see that associated with the Borneo vortex, we have precipitation occurring in the north-northwest of the Borneo vortex, but not in its center. And that's aligned with the brightness temperature from Himawari. If we look at the precipitation from the 4.4 kilometer model, we can see that the model is also producing precipitation in this comma-shaped band in the north-northwest of the vortex center. So it does a pretty good job at capturing this event. The global model is not quite as good. Precipitation is much more widespread, generally weaker, but it has a maximum in the north-northwestern part of the vortex. So overall, this is doing a pretty good job at capturing this event. So to compare it a little bit more, we're looking here at time series of the relative vorticity and the precipitation following the vortex. So the black line is the 4.4 kilometer model, the red line is ERA5, and the blue line is the global model. And you can see that the convection permitting model does a pretty good job at capturing the evolution of the relative vorticity throughout the lifetime of the vortex. The global model is not doing a bad job either. It's not great at the end, it's not perfect, but it's doing a reasonably good job. It looks a bit different if we compare precipitation. So this time the red line is GPMI merge precipitation. And you can see that the convection permitting model is able to capture the diurnal cycle pretty well, where the precipitation occurs during the day. And if you look at the global model, it's not doing such a good job. That's not a surprising result. Lots of studies have shown this. Due to the convective parametrization, the global model can't capture the diurnal cycle of convection well. But apart from that, both simulations are doing a good job. So we want to use them to look more into the structure of the vortex. So if we start here on the top left, what you see here is the meridional winds. You can see the northerly winds, the southerly winds. You can see the cyclonic circulation around the center of the vortex. The plot at the bottom shows the total precipitable water, and you can see that this is a moist vortex, has a lot of total precipitable water. You find a maximum in this region. If we now take an east-west cross-section through the Borneo vortex, this is what we have here on the left-hand side, and look at the same fields, you can see total precipitable water is not only maximum here, but it extends through higher levels in the troposphere. And if we look at the meridional wind, you can see it going into the page, coming out of the page. You can nicely see the cyclonic circulation associated with the vortex. The black contours here are the isotropes. You can see for most part of the troposphere, they're almost flat, but around the Borneo vortex, pretty much on the vortex scale, they are bowing around this anomaly, and this is typical for a warm core anomaly. Before we dive a bit more into the dynamics of this vortex, we want to look at the large-scale environment that characterized the large-scale environment in which this Borneo vortex developed. At the top, you see the large-scale background flow, and this is averaged for the entire duration of the global simulation, and we also average pretty much over the entire maritime continent. You can see it's a pretty wide averaging band. And what you see here, that the large-scale background flow is mainly easterly. And you can see it strengthens strongly with height up to a maximum about 7 kilometers, and then it still increases a bit, but much weaker. And this is very typical situation for the winter monsoon in Southeast Asia. And we also have here the cyclonic shear on the southern flank of this stronger vertical shear below 7 kilometers. Now, the variable that we plotted here in the, at the bottom is R times N squared. So R is the specific humidity, N is the static stability. So this is basically a moisture stability variable. If we have regions where R times N squared is large, that means the air is moist and unstable. And if R times N squared is low, then the air is drier and more stable. For example, here, you can see it's high. This value is high near the surface, then it decreases, and then we have here this region where the R times N square is increasing, and that is basically located between 5 and 4.5 kilometers. So we're having here this vertical gradient in moist stability interface, or this moist stability interface. And you can also see this turquoise lines, and the turquoise lines are that part of the vertical velocity that is associated from diabatic heating. And you can already see there's a wave-like pattern, and this wave-like pattern looks like a diabatic Rossby wave that is propagating on this moist stability interface in a region of very strong vertical background shear. And we will come back to that and what role that plays in the formation of this Borneo vortex in a second. First, we want to look at the output from the SGT tool. So on the top left, you have the global MET-UM, and what we see here is the 1 hour accumulated heating at 7 kilometers, and the winds are the horizontal winds at 2 kilometers. On the right-hand side is the full output from the SGT tool, and in all the SGT plots we see, or tool plots, we see the vertical velocity. So this is the total vertical velocity, and we have the winds from that run. So we can only qualitatively compare these two, but what we can see, the cyclonic part of the vortex is present in both of these, and we can see we have this area of heating in the northwestern part in the global MET-UM, and we also see it in the SGT tool. And this is similar to what we've seen at the beginning from the satellite images. This is where we get the precipitation and the convection occurring. So by comparing these two, we can already see that the Borneo vortex is in semi-geotriptic balance. So we're now using the tool to look at the forcing terms, and the forcing terms are shown here at the bottom. So this one, bottom left, shows us the vertical velocity associated with diabatic heating. It's basically the turquoise contours that we've seen on the previous slides. And you can see that we get the positive anomaly exactly in the same region where we've seen the heating. So all this vertical ascent comes from diabatic heating. Also shown here are the wind vectors. They are the ageostrophic wind, and you can see that they're kind of converging in a southwest and northeast direction underneath the heating maximum. So
Ageostrophic balance, and yet you're extremely close to the equator.
Yes.
So how?
We excluded everything around 0, where F is really small. We didn't apply the tool there.
I've seen some plots where you say ageostrophic very close to the equator.
Yeah. So I've forgotten the details, but we used a blending zone and error, and we've done. Let me look it out afterwards. I can't remember the details, but we blended it out so it doesn't give us any non-linearities. We go to in the southern hemisphere. But the ageostrophic wind flow, I wouldn't say it's not a concern because the forcing doesn't come from that at all. You can see it's almost 0. But yes, it's an obvious question. We're using but we are still far. We're still far enough away from the equator, right? F is not 0.
How far away do you think you need to be?
I think we decided that we're definitely between 2 north and 2 south. We wouldn't apply it. So I think for any of the other Borneo vortices that I showed you before, you can't really use it. It's too close to the equator. Yeah. But even though, right? This is a valid concern, it does a pretty good job, right? It represents what we see. And if you look at the ageostrophic flow again, we can see that it produces winds that are actually anticyclonic. and therefore reduces the total flow, and that means that in this case, the Bernoulli water is actually slightly subdued stronger. Okay, so let's look a bit more at the vertical structure and the evolution of this case. All the plots that I showed you previously, they were for, I think, the 23rd of October. Now we're going a day back in time, 22nd of October. And what you have here is the cross-section through the vortex, showing the meridional wind and the potential vorticity, and the turquoise lines always show you the vertical that part of the vertical velocity that comes from diabatic heating, which we just seen is pretty much all of it. So we have here, we have our Borneo vortex that we can't really see yet, but we're looking at the diabatic Rossby wave that is forming at mid-levels. We have here the cyclonic circulation. We have the maximum in diabatic heating, which is indicated by this blue diamond. And we have the maximum in potential vorticity, which is indicated by the purple triangle. And you can also see that this maximum is not just confined to 7 kilometers, it extends below and also extends above this 7 kilometers. And as a condition for or characteristics of a Rossby wave is that the PV and the meridional wind, they have to be in quadrature to each other. And you can see that the PV maximum is east of the maximum or of the zero line of the meridional wind, and also or in other words, the diabatic heating maximum is west of the PV maximum. So this is what you would expect from a Rossby wave. And you can see that both of these maxima, they are occurring vertically aligned with the formation of our Borneo vortex. If we look at the same fields now at 7 kilometers, you can see that all this development happened here on the southern flank of this subtropical anticyclone. We are in a region of a northeasterly surge, cold surge, and this is where the development of these diabatic Rossby wave was happening, and also our Borneo vortex. And you can already see that the horizontal flow is moving, it's already slightly having a wavy behavior. If we look at the evolution now, this is 12 hours later, and we're only looking at the meridional wind here in the horizontal and the vertical, but the symbols mean exactly the same thing. So you can see now the wavy behavior even more clearly. You can see the diabatic Rossby wave at 7 kilometers, and we can see that the Borneo vortex is just starting to form, but it's weaker and they're vertically aligned. 12 hours later, you can see that the Borneo vortex is strengthening. We can also think of it as a thermal Rossby wave near the surface, and the diabatic Rossby wave at 7 kilometers is intensifying. And now you can really see the wavy behavior or the wavy pattern in the horizontal flow as well. If we go forward 24 hours more, we can see that this tilted configuration has now enhanced, and you can see that the Borneo vortex is starting to weaken and the diabatic Rossby wave is intensifying still. And here you can see really nicely that they have separated quite a lot in terms of their location. So what seems to be happening is that while they were aligned with each other, there was an interaction of the different types of Rossby waves, the lower that aided the Borneo vortex to form in this case. They weren't able to phase lock, diabatic Rossby wave was moving faster, and our low-level thermal wave was decaying. And we could also calculate the phase speed for these two Rossby waves, and we've done this by starting with the Ertel's potential vorticity, linearized about the basic state, and we used the large-scale rain approach outlined in De Vries, and this is what we got. And maybe the key point here is that the diabatic heating term is proportional to the vertical velocity at the result of was coupled with the resolved vertical motion. And G here is the basic state moisture gradient that the diabatic Rossby waves are propagating on. And you can see here we have this term R times N square over dz, and this is what we were looking at in one of the cross sections prior, that they're propagating on this change of the moisture or vertical moisture gradient. You can solve this equation and get a phase speed for the upper level wave, our diabatic Rossby wave. It looks like this. U is the zonal flow along which the upper level wave propagates. This is the meridional, and this is the vertical PV gradient. G is the same as here, and this is the contribution from the lower level Rossby wave that you can as they're interacting with each other. And then once we had this, we estimated how they're propagating and how their propagation speed compared to what we've seen in the simulation. And we've seen basically what we just seen in the snapshots or in a couple of 3 slides previously, that the diabatic Rossby waves at mid-levels, it was propagating on this moist stability interface that we saw that occurred between 4.5 and 5 kilometers, and that our Rossby wave, a warm temperature thermal Rossby wave, which we think of as our Borneo vortex, moved at slower speed, also propagated to the west. At beginning, they were aligned, positively interacting with each other, but then as the diabatic Rossby wave moved at a faster speed, they couldn't really phase lock, and the lower level Borneo vortex then weakened and decayed. So all the work that I've shown you so far is pretty much old work and published, but I just wanted to show you a little snapshot that this is still something that we're thinking of. There are not many results yet, but we want to look more into the dynamics of what happened into the other different Borneo vortex types. And one that we're particularly interested in is the C-shaped vortex cluster. And we want to using convection permitting simulations to investigate how is the convection linked to, where does the convection form, where it forms in the Borneo vortex. And this is the work of a PhD student who only just started a couple of months ago, so that's why we haven't much to show yet. But what I can show you is that these MED-UM simulations that were run actually from Singapore Weather Service at 4.4 kilometers as well, are able to capture this Borneo vortex and the associated convection and precipitation pretty well. So this time stamp that I show you here, this is quite far into the simulation. It's the same vortex that you've seen before, but you can see that the location and not so much the intensity, but the location of the clouds and the precipitation is captured quite well. If you look at the relative vorticity and we compare this to ERA 5, obviously the field is much noisier, but overall the convection permitting simulation seems to be doing a pretty good job at capturing this event. And even if we look at day 5, it's doing a reasonably good job at capturing this event. And the sorts of things we want to investigate are, where does the convection occur and why? It doesn't always occur in the northwestern part of the Borneo vortex. And also, what's the role of orography? So you can argue possibly that the high orography in this region might channel the flow. So we would like to run some experiments where we flatten the orography, and we would like to look a bit more in a dynamical sense and not in a statistical sense, as we've done already at the different Borneo clusters, and how are they linked to heavy precipitation. And this brings me to the end of this talk. So what we have seen from this case study in October 2018, that for this case, the convection was located in this comma-shaped band in the northwestern part of Borneo. It moved in east-westward direction through the South China Sea, and that the SGT tool showed us that the vortex is in balance despite being so close to the equator. We've also seen that for this case, the setup comprised the low-level thermal vortex and the mid-level vortex, and that the mid-level diabatic Rossby wave was propagating along the moist stability gradient. And we also seen in these cross-sections that there is a coherent signature in this diabatic Rossby wave in PV, meridional wind, and also in the vertical velocity fields. And the vertical motion is dominated by the coupling with diabatic heating and is shifted relative to the PV. We also seen that, so that as a result, the diabatic Rossby wave is propagating towards the west, and at a propagation rate that is consistent with the prediction for moist geostrophic theory. And the initial development at the low levels was consistent with the barotrinic growth, with both the alignment of both the upper and low level wave. And keep in mind that this happened in an environment that was characterized by high baroclinic shear on the southern flank of the cold surge. Then the climatological work of the Borneo vortex tracks showed us that Borneo vortices are more likely to occur. They're more likely to occur on days where we have strong cold surges, and if we have weak cold surges, they're more likely to move in an east-westward direction through the South China Sea and can affect Thailand and Vietnam as well. We've seen that the MJO is not so important at modulating many quantities of the Borneo vortices, but they are have an impact on the rainfall. When it came to equatorial waves, the biggest impact on the rainfall was from the Kelvin waves. It was the mixed Rossby gravity waves and the n=1 Rossby wave that strongly modify the frequency, the rainfall, and the vorticity, because they're modifying the environmental flows in that region and also the relative vorticity. And these properties were found to be highest when the Borneo vortex was located at the leading edge of the wave phase. And we also seen, even though I didn't show you this, that if the vortex was located north of 4 degrees, then they tend to move along with the mixed Rossby gravity wave or the n=1 Rossby wave. And actually, I wanted to show you this, but I forgot to point it out on one of the Hofmüller plots, where the vortex actually that we looked at, it was aligned with the traveled for a bit with the positive phase of an n=1 Rossby wave. And hopefully you have seen from this talk that the term Borneo vortex doesn't only mean that is the vortex that occurs in the northwestern part of Borneo. It also includes those move in east-westward direction through the South China Sea and those that cross into the southern hemisphere and take their cyclonic rotation with them. But they all have a very similar structure and are really the same thing. And with that, I would like to thank you for your attention and happy to answer questions.
I would like to know if people online can ask questions. They should just raise their hands. Okay. So yeah, everybody online, if you have questions, just raise your hand and we should be able to see it here.
We have one in the room.
Yeah, we have one in the room.
Yeah, very interesting talk. So a lot of information to digest. I have two questions. The first one is, over the maritime continent region, I believe there are strong interactions among the cold surges, the MGO, and other equatorial waves. So how much do you think your study can clearly separate their individual impacts versus their strong interactions?
Good question. We haven't looked at this, and part of one of the projects, our project partners in Reading, they are looking at what happens if you get superposition, well, not a superposition, because it's not a superposition of different types of equatorial waves and cold surges, and how that impacts MCSs. But you're asking how big the contribution from each of the type is on modifying the Borneo vortex, is that right?
Yeah, by ruling out their interaction, like.
Well, we haven't looked at the interaction at all. I have completely ignored it. I have no feeling for this. All I know is that if the positive phases overlap, it's not just a positive, it's not just a superposition of effects. I have not looked at it at all, but it is interesting.
Okay, thank you. Yeah, my second question is, like, you're looking at the larger scale, like circulation, their impacts on the Borneo vortex. I know that is interesting work. Do you think you have planned in the future to look at smaller scale impacts, the up scale impacts on the Borneo vortex? Because I think there might be strong variations in the cycle precipitation, the topographic effects of topographic gravity waves, and other smaller scale events. Do you think they will have strong impacts on the Borneo vortex?
And I could very well imagine that the diurnal cycle has a big impact on the convection associated with the Borneo vortex. I could also imagine, depending where it occurs, that maybe it's interaction with land sea breeze circulation. And that's exactly why why we need to do more work on investigating the Borneo vortices. I could very well imagine that's an impact of the orography. There are really high mountains in this region. There's always the theoretical argument that there's already channeling the flow around the Borneo vortex. And I don't have an answer, but all I can say that these are the kind of questions we hopefully can address in this PhD project.
Cool. Thank you very much.
Can I ask a question similar to that? You know, one of your diagrams, maybe the third one, there was a huge effect of the MJO. And I would like to know, what is that directly due to the MJO? I could very well imagine might be because you get vortices generated by MJOs, so, which contribute in a different way, but it contributes the cyclonic vorticity, for example. That, I think that's it. That was, no, another one.
Another one?
I think there was that
Oh,
one
this was
later.
Not from us, from
Uh,
a different study. Maybe you mean this?
No, there was one with a very, very big signal with an MJO attached to it.
Okay, I think the only MJO plot I'm showing is this one.
I think. Well, I don't know.
Okay.
We can talk about this at 4 o'clock.
Yeah, we can talk about it. So what was your question? How big the impact?
Well, no, the MJO has a big effect. There are vortices generated by MJOs, and some of them can shed, even cyclones.
Mhm.
And these are very, very strong precipitation events. And that alone from the MJO, I would say, is a bigger signal on rainfall than even the Borneo vortices.
Right.
I'll show you in an hour or so what I mean.
Yeah, that would be good.
Yeah.
We definitely did not separate this, right?
I see. No, okay.
No, we only tracked vorticity maximum.
Yes, I see. So you don't know where the vorticity came from.
Exactly.
Ah,
Exactly. And that's why the only case where we had the chance to look into it in detail was the one I showed you just now.
I
with
see.
the Intact with diabetic.
yes.
retinopathy.
Well, what I can do is identify that vorticity signal.
Yeah, that would be really interesting.
I'm just wondering, given this link with the cold surges and amplified warming of high latitudes, has anyone looked at whether if cold surges are becoming less cold, does that impact on these vortices?
I don't think, well, there is one study by Juliane et al. And Kato from Exeter University, where they looked at these the same way and they looked at them, how they behave in CMM6 models. It's the only other study that I know, but I've forgotten how they behave in those climate models.
Is this DJF or?
Yes, because they only occur in GJF. During boreal winter, you get the flow from the southwest, and they don't occur. It's a winter thing.
Okay.
But we were motivated by looking at them because in these projects we worked with the weather services in Malaysia and in Vietnam, and they always told us they bring us so much trouble. They're so hard to forecast. We want to understand them a bit more. So this is what's all kicked off, basically.
It looks like we have a question online. Go ahead, Rubaiyat.
Hi, great talk. So I have a question about the precipitation forecast. So you had a comparison with a 4.4 kilometer regional and a global forecast, and you seem to have a conclusion that the global forecast doesn't work very well because of the convective parameterization. So I was wondering if you were, or any of your colleagues were able to do a global, let's say 2 kilometer or 1 kilometer, like convective scale simulation without the convective parameterization. And do you think like how comparable or how different are they when comparing with the same resolution of regional MET model?
Yeah, that's a good question. So we haven't looked at this. We would like to generally analyze those simulations, but where we're not available for this particular case, it's not too old. You should also maybe keep in mind that, I don't know if anyone noticed, maybe John did, these are old simulations, right? They're all run with a pretty old configuration of the model. So now the method is using what they call the RAL3 and GA6 something, I've forgotten the number. So I think the models are performing already better as they did back then. I mean, you would hope, but obviously you have to investigate if the global convection permitting simulation is doing a better job. It's definitely more noisy, but I'm not sure if it solves all your problems. It would definitely be interesting to investigate. But this problem that you see on this slide, this is a very common, often diagnosed in many studies, issues that the global model is not capturing the diurnal cycle. I'm not sure if that answered your question or not.
Yeah, I think you did. Okay, thank you so much.
Thank you.
Uh, uh, Does just lateral gradient in drag, is that an important source of vorticity for this?
Quite
vortices?
possibly. So that's one of the experiments we would like to run to change that. I don't know.
I was wondering if there's like carbon vortices.
I've not seen indications of that in any of the fields that I looked at.
Okay, okay.
Yeah. But anyway,
All right. So, it's 2:00. And before everybody online leaves, I want to make sure that people at RAL and M-Cubed are aware that, Juliane will be down at Foothills tomorrow and Thursday morning. There is a sign-up sheet to meet with her. Please contact Nancy Sue, if you haven't received, a link to the sign-up sheet. And for people here in CGD, Juliana will be back on Thursday afternoon and on Friday morning, and there's also a sign-up sheet, which you should have all gotten in the mail several times. So I just want to thank Juliana again. Thanks everyone for showing up.